So Max Born, 1926, introduced the probability rule. While he did not explicitly invent the word collapse, Max Born introduced the Born rule. He proposed that the wave function does not represent a physical smear of matter, but rather a probability wave. He established that if you square the absolute value of a wave function's amplitude, you get the exact mathematical amplitude of where a particle will snap into a reality during an observation. So this must lay the foundations for how is square translate into a single outcome. So we have the Oxburn's probability rule here. So this simulation illustrates Max-Born's probability rule in year 1926, one of the foundational principles of quantum mechanics. So what you are seeing, the graph shows two different quantum states of wave functions. We have the blue curve, left peak centered around x equal to negative 2.5, so a relatively narrow wave functions. And we have a green curve, right, centered around x equal to approximately equal to 3, wider wave functions. So we can have the histogram here. So this one, histogram. Uh, so the gray histogram of bars represent actual measurement outcomes. So where particles were detected. So a red curve is the small probability density, the square of the absolute value of the wave functions derived from the wave functions. So Max Born rule explained. So in 1926, Max Born proposed that the square of the wave functions amplitude gives the probability density. That is the square of the absolute value of the wave functions. So this was a revolutionary idea. Before Born, the wave function was mysterious. Born realized it was not a physical wave of matter, but a probability wave. So how the simulation works? So observe one particle here. The particle randomly appears at one position. Uh, at one position, the particle randomly appears at one position, choosing according to the probability distribution, Born's rule. So you will see one bar light up in the histogram. So observes 500, 500 particles. It runs many measurements. So as you add more particles, the histograms builds up and starts to match the shape of the probability density, the red curve. So this demonstrates how quantum randomness produces statistical patterns. Then clear reality. So we can clear this. So wipe out the histogram so you can start over. So the key insight here, this demo teaches individual events are random. So you cannot predict exactly where one particle will be detected. So the probability distribution is predictable. So with enough particles, the pattern matches the square of the absolute value of the wave functions. So different wave functions here, uh, meaning different probability distributions. The narrower blue wave function gives a tighter cluster of detection. The wider green one spreads them out. So connection to the previous image here. So we have the first image, this one. So the first image here, the Heisenberg wave functions, reductions, showed a wave function collapse, how spread out possibility becomes a definite position upon measurement. So this image explains the probabilistic nature of that collapse. where the particle is likely to appear is governed by Born's rule. Together, they show the core mystery of the quantum mechanics. So the wave functions are evolved smoothly and deterministically. But when measured, it collapses probabilistically according to Born's rule.